surface, and we talked a lot about how that air changes temperature as it rises, how it behaves, condensation, adiabatic cooling, and then we applied that idea to the concept of stability. But one thing I haven't touched on yet is, so we talked about how in unstable air, if an air parcel is forced off the ground, if it's pushed up somehow, it continues to rise. Whereas in a stable environment, if that air is pushed off the ground, it just sinks right back down. But the one thing I didn't really talk about is, how do we push parcels off the ground in the first place? We don't have evil villains here at the surface like Gru, paying his minions to push the air up. So what actually does push the air up? Well, that's actually what this lecture is going to cover. So, as I just mentioned, when air parcels are forced up, they'll sink if the air is stable. Just like the ball in the valley. If you nudge it in either direction, it just comes back to its original position. And then in an unstable environment, if you take that same air parcel and push it up, it just keeps rising, just like the ball on top of the hill. But what forces the air up? Well, believe it or not, there's actually 4 natural causes of rising air. And these 4 things are 4 things that we as meteorologists look at, because when these are present, when any one of these 4 is present, it can give us the hint, it can give us the idea that, hey, we're going to get some cloud development today. We're going to get some rising air, we're going to get some cloud development, and then in the next 2 lectures, we'll actually talk about how that leads to precipitation. So, without these mechanisms forcing the air to rise, stability wouldn't matter at all. It wouldn't matter how warm or cold the air aloft is. And aloft just means high above the surface. It wouldn't matter. So without these forcing mechanisms, without these nudges pushing air up, none of what we talked about in the last 2 lectures would even matter. Now here's the good news. For what I'm about to talk about, there's no calculations, there's no theory. It's just 4 very practical things that we actually experience in our everyday life. And this will actually give you a little insight as to why we get rain sometimes, or why we don't get rain other times. So here's what the 4 are. There are 4 main mechanisms. The 4 mechanisms are, first, convection. And this one should come as no surprise to you. The ground gets really hot, it heats the air right above it up, and then that air rises. So that's what convection is, just like the bubbles in a pot of water. Convection is simply just this warm air that's forced up. But that's not the only one. Mountains, topographic lifting. If you have air that hits a mountainside, it has nowhere to go but up. And as it goes up, depending on the stability of the atmosphere, it can keep rising. And in fact, this actually causes some regions, like the Front Range of the Colorado Rockies, to experience thunderstorms on a regular basis. Convergence, we're going to talk more about convergence in the next module when we talk about low pressure systems, but convergence is a key component here, or a key forcing mechanism. And convergence creates low pressure, and this is why we actually see rainy weather around low pressure systems. And then the final one, fronts. And I'm talking about warm fronts, cold fronts, occluded fronts, stationary fronts. Along a front, one air mass is forcing another air mass up. And it's usually the warm air mass that's being forced up. And as that warm air mass rises, it expands, cools, and condenses. So those are the 4 things. And so this little image here just shows each one of them. And for the next 10-ish minutes, I'm going to talk about each one in depth. And then for this week's discussion question, I'm actually going to bring up an interesting real life application that we see here in the Bay Area. So if you live here in the Bay Area and you're familiar with the geography of the region, this is going to make a little sense to you. If not, that's okay, we're going to talk about it. So first off, let's talk about convection. So if you remember from Module 2, convection is the vertical transfer of heat. So basically what happens is the sun heats up the ground, and the ground heats up the air just above the ground by conduction. Now the air is a poor conductor, so the heat can't really travel too far. However, what you do have is you have this very thin layer of extremely hot air. And hot air likes to rise. And so as this hot air rises, it forces colder air from higher up back down to the surface. And then that colder air gets heated up by the ground, and then it rises. And so you get these convective bubbles of upward motion. Well, if you recall from the last 2 lectures, as air rises, it expands, cools, and condenses. And hence we get clouds in this particular situation. And as a matter of fact, during the daytime, many locations east of the Rocky Mountains experience a tremendous amount of convective thunderstorms. A tremendous amount of these thunderstorms that just form from hot rising air. And we'll talk more about that in a few weeks when we talk about thunderstorms. But this is actually how thunderstorms can just pop up out of nothing, even without a cold front or without a low pressure system. Just with lots of heat near the ground, boom, you get thunderstorms. So, and this image just sort of draws on that a little bit more. Again, you get a really warm surface, especially some areas heat up a lot more than other areas depending on vegetation cover, depending on the presence of trees. There are many things that can force air to become warmer than around it. And then remember, if the air is warmer than the air around it, it rises. And then as it rises, once it reaches that lifted condensation level, you get clouds that form. Now, we actually have an interesting phenomenon here in the Bay Area. And if you've ever been to Santa Cruz, and you've ever noticed that it feels cooler and cloudier there than it does in, say, San Jose, Cupertino, the Silicon Valley area, it's because of something called orographic lifting. So let me explain what's happening here. So right next to Santa Cruz is the ocean, right? And during the afternoon, winds blow from the ocean onshore. We call that a sea breeze. We're going to talk about that more in the next module. Well, as that sea breeze hits the mountainside of the Santa Cruz Mountains, if you've ever been to Santa Cruz, you know that there's some mountains a little inland. Well, as that sea breeze hits those mountains, that air then rises up. And there's usually a lot of moisture in the air. And so as the air rises up, it condenses. And so the area facing the ocean where the winds are coming on, this is what's called the windward side. Remember that word. It's the side of the mountain that faces the wind. Write that down if you need to. The windward side of the ocean, windward side of the mountains, forgive me. Clouds commonly form here. Now, something interesting does happen though. Because as those clouds form, moisture has condensed. And what I talked about in the last 2 lectures was this idea that as air rises and it cools and condenses, I kind of gave this rule called the Las Vegas rule, that whatever happens in the parcel stays in the parcel. There's actually one exception to this. There's one exception to this that you need to know. And that is, once moisture condenses, it has transitioned from a gas to a liquid. It is no longer a part of the parcel. These parcels are simply air parcels. They're parcels made out of gases. Once moisture condenses, it is no longer part of the parcel. So it just hangs out. Usually as cloud droplets. They may get big enough to form rain droplets and fall to the ground. But once the moisture condenses, it is no longer a part of the parcel. So what's actually happening is as air rises up and over a mountain, it actually loses moisture. It loses moisture. Now this isn't a problem for saturation because the air is getting colder, therefore the dew point's getting colder, so the air remains saturated, but it loses moisture. And it'll keep losing moisture until it stops cooling. That usually happens when the parcel of air reaches the top of the mountain. And then if the atmosphere is stable, the air then rolls down the other side of the mountain. You can again think about like a ball on top of a mountain in a stable atmosphere. Well, actually, that's not a good analogy. In a stable atmosphere, the air that's forced up has to sink back down. So it sinks down the other side of the mountain. Now, one of the things that's really interesting, though, is remember, moist air and dry air cool at different rates. Moist air cools at a rate of 6 degrees Celsius per every 1,000 meters, whereas dry air cools at a rate of 10 degrees per every 1,000 meters. Now, the opposite is true, too. Moist air also warms as it sinks. Moist air warms at 6 degrees Celsius per every 1,000 meters, and dry air warms at 10 degrees Celsius per every 1,000 meters. So what actually is happening is as air goes up the mountain, it's not cooling very fast. And its moisture's condensing and so clouds are forming. However, as it sinks down the other side of the mountain, it quickly compresses and heats up. But because it's unsaturated on the other side of the mountain, because it's lost all of this moisture, it warms at a much faster rate. So by the time the air reaches the other side of the mountain, what we call the leeward side, that's the side facing away from the wind, the air becomes really hot and really dry. Now, with that said, for this week's discussion, I'm going to give you a little bit of a hint, and then I'm going to have you explain this more in the discussion. And the purpose is just to reinforce this concept. But if you live in Santa Cruz, you're on this side of the mountain. This side is called the windward side. Winds are coming from the ocean, hitting this side of the mountain. They then rise up and over. They cool, condense, form clouds. And then as the air peaks, it then sinks down the other end, quickly compressing and warming. Now this gives us a pretty interesting consequence. And I'm just going to say this real quick. And what this actually creates is this creates a situation where the windward side of the mountain is usually much cooler and much wetter, while the leeward side of the mountain is usually much warmer and much drier. And believe it or not, Santa Cruz gets about twice as much rain annually as San Jose does. And it all has to do with this rain shadow effect. So the next thing we're going to talk about is the idea of convergence. So think about what would happen if a car was coming from all directions at an intersection. So you had a car coming from the west, a car coming from the east, a car coming from the north, a car coming from the south, and they all collided in the center of that intersection. Well, what you would get is basically a giant pileup, right? And hopefully nobody ever has to experience that here. But when you have wind coming from all different directions and it converges at a single point, that point then results in a lot of rising air, because once the air converges, it has a lot of momentum. It's got to go somewhere. It goes up. And as it goes up, the usual drill then happens. You get cooling, condensation, and cloud formation. And this is common around low pressure because in low pressure, air converges. Now, we're going to talk more about why in the next module. But just for now, just trust me, air converges at low pressure. And then that converging air rises, and that rising then creates cooling, condensation, and rainfall. So this is why we get a lot of rain around low pressure systems. And then the very last lifting mechanism, the very last cloud formation mechanism, actually comes in the form of frontal systems. Now, frontal systems will actually be talked about in two modules. Module 7 is when we talk about fronts. And fronts are a big deal because they act like weather makers. So think about some of the most interesting weather that you've experienced, whether it was a really, really rainy day, a severe thunderstorm, a tornado outbreak, a hurricane, or anything. Most of those things are caused by either low pressure systems, which was the previous slide, or fronts, which is this slide. Well, basically what happens along a front is you have two air masses. You have a warm air mass, which is very light in its density and it rises easily. And then you have a cold air mass. Cold air is dense, it's heavy, and basically what happens is as these two air masses clash, think about a football player tackling another football player. The cold air essentially undercuts and tackles the warm air, and then the warm air rises up and over. And this warm air is usually heavy in moisture. So along fronts, warm air is forced up, so it expands, it cools, and it condenses. So again, the same drill. So warm air is forced up where it expands, it cools, and condenses. Now in the case of some fronts, specifically warm fronts, the air is usually lifted very gently. And so clouds spread over a large area, and they're typically not very intense rainstorms. On the other hand, in the case of a cold front, the air is actually shot straight up. And in this case, you get these large towering clouds called cumulonimbus clouds, which create a tremendous amount of rain. It creates a tremendous amount of rain. We're going to talk more about these fronts in the next few weeks. But again, the reason why we even care about them is because along a front, warm air is forced up and over cold air. And depending on the angle that it's forced up, you could either get very layered stratoform clouds. Usually that happens along warm fronts. Or you could get very, very tall, stormy cumulonimbus clouds. Typically that happens around cold fronts. So, just to review, there are 4 things that lift air above the ground. And those 4 things are, once again, convection, just warm air rising. Topographic, air being forced up and over a mountain. Convergence, that's low pressure, air converging at low pressure. And then frontal lifting. And so that's it for this lecture. In the next 2 lectures, we're going to talk about how those condensing water droplets can then turn into something I love, which is rainfall. So we'll do that in the next lecture, in the next 2 lectures, and then that'll wrap up this module. Until then, I'm Terrence Mullins. Thank you for watching.